Hello everyone and welcome to this week's Seds Online webinar. We're really pleased to be able to offer all of these events to you for free thanks to generous sponsorship from the International Association of Sedimentologists, the IAS. This week we're really pleased to welcome Gloria. She's a quaternary geologist and a geochronologist with expertise ranging from geoarchaeology to tsunami geology. Gloria completed her Masters in Paleoseismology at the University of Victoria in 2002 before completing a PhD in geochronology at McMaster University in 2007. Gloria then worked as a field geologist in Canada and in 2005 took on a role as scientific consultant at AU University in Colombia. Since then, she went on to work as a coastal engineer before joining the faculty at McMaster University. And since leaving McMaster University in 2010, she has undertaken a range of academic positions in Israel. She presently works at the University of Haifa and the Institute of Maritime Studies and was head of the Luminescence Lab in Spain until last month. So today, Gloria is going to be giving us an introduction to OSL dating and luminescent signals. So without further ado, I'll hand over to you, Gloria.
Thank you, Catherine. I'm really excited to be here today and to share with you a little bit about what is this deal of OSL dating and luminescent signals. Perhaps some of you already know what OSL dating is. So this webinar is going to be a basic introduction to OSL dating. And I'm going to show you later on a range of applications that are quite new and very keen for sedimentologists actually. And it's, I think we need in this OSL community of ours, we need more sedimentologists to get their hands into these so nice applications. So without further ado, let me see. Wait. There we go. So I always like to start my talks with this beautiful little paragraph of the Auguries of Innocence poem by William Blake, because I think it defines, as I said in the abstract, it defines what OSL is. We're actually looking at singular grains of quartz or feldspar, and sometimes even zircon, apatite, or calcite, and retract or extract electrons that are produced in the environment naturally. And with those electrons, we're going to actually determine the last time the grain has been buried. So a single grain of quartz or feldspar can actually tell you the precise or very quite accurate age of a sedimentary deposit. Obviously, the range of applications are enormous, and it's one of the very few dating methods that has grown exponentially quite fast over the past 30 years. So as you can see, you can go from geology to natural hazards, paleoclimate, paleoseismology, dosimetry, radiation sciences, archaeology, basically a whole range of applications that many of us as geologists or as sedimentologists, we do in a daily basis. So luminescence has become, I would say, the leading dating method right now, surpassing radiocarbon, because it's so, it exists all over the quartz and feldspar exists all over the surface of the planet. And if you understand well the physical processes that form all these sedimentary deposits, you can actually accurately interpret the environmental archives and date them. So a fundamental requirement for this is that you understand the physical processes from which you're going to take samples from. So in luminescence, well, this thing started with physicists. And only now, as geologists got into the community, we are understanding the power of OSL in terms of, in order to understand physical processes. So these time-dependent physical processes and predictable accumulation changes are really good for OSL to be used with those. So basically, we need more sedimentologists into the community. And if you apply various methods into the obtaining numerical ages from all of these different sedimentary deposits, or if you want to understand the rates of processes, it's even better. So the strength of understanding physical processes relies on the overlapping of several numerical dating methods, basically. But today we're going to see only OSL. I'm not going to start comparing with radiocarbon or other methods because it's been proven already the reliability of OSL quite well. I'll show you a couple of slides with that. But as I said before, you can apply OSL in basically all sedimentary environments that you can think of, from glacial deposits, exhumation rates, burn events even, to the depths of the oceans like marine deposits, raised beaches, archaeological sites, slope deposits, landslides, for example, fluvial deposits, lakes. So as you can see in this image, we can basically work everywhere as geochronologists, experts in OSL dating. The problem is that you have to understand the processes occurring in each one of those environments in order to determine whether it's feasible or viable to use OSL dating in those environments, because they're not going to, the sand grains are going to suffer different geological surface processes. And according to those surface processes, you're going to have what we call better bleaching or not. And we try to go for the sedimentary environments that have been very well bleached by sunlight. Those are the best, basically. You get into a lot of problems, but it's doable. Dating is doable when you go into environments that are less predictable to be well bleached. And we're going to see some examples of that. So those are the problems that we have to face depending on the type of sample and the type of environment that we date. So a brief history of OSL dating. So as you can see, like basically this method started when Boyle started basically doing experiments about the optics of minerals. Then you have to have the invention of the photomultiplier tube, otherwise we would be doomed. Like this is the most essential part of the reader, the luminescence reader, because it's going to capture all the luminescence coming out from the electrons. Then we started by, or the luminescence started with the detection of thermoluminescent signals from pottery, and then Aitken in 1964, as you well know, because this is very well known and applied vastly in archaeology. The first TL dating techniques to date fire pottery were done by him using TL. Then there was the development of the reader, and then the first TL ages of sediments, and in 1979, but then in the most important part, or the key part, is that in 1985, David Huntley from Simon Fraser University in Canada understood that you could actually capture luminescence signal from inorganic material. In order for us to apply what was only applied to ceramics to nanoscience. And with the later development of the SOAR protocol in the year 2000 by Murray and Wento, we started to basically standardize the measurement procedures, which is extremely important because the more standardized the method is, the more reinforcement of the application you will have. And then we can also compare ages among the different labs and experts. And over the past 5 years, or sorry, the past 10 years, the development of protocols and instrumentation has been astonishing. So now we do OSL thermochronometry. Some labs and some experts do OSL thermochronometry. We also extended the maximum age range down to 1.2 million years with VSL, violet stimulation light. We are now doing applications or dating rock surfaces and even dating calcite. So it's been quite a long history in, let's say, of the development in fairly short time. So this is the infamous apparatus that we use. It's a luminescence reader. It's commercialized by RIIMS, DTU RIIMS in Denmark, but Freiberg Instruments in Germany also has another prototype, a little bit very different from this one. It's like a green box, but I'll explain to you like the parts here. So it's basically a black box in which you have a carousel in which you're going to put these little discs that are going to hold your grains of sand. And the key part here is that this electronic control box controls the entire operation from whatever you tell the computer to do. So it's going to have a beta source that is going to apply radiation into the samples. And as soon as or after you measure the natural dose in front of the grains themselves, like the first measurement is always the natural, then you repeat those radiations and you repeat measurements or readings with the photomultiplier tube, which here you have the sketch. A photomultiplier tube has right underneath it a series of LED lights, infrared and blue, to excite the electrons trapped in the little grains. So IR LEDs excite feldspar grains and blue LEDs excite quartz grains. So this is a better schematic image of the internal part of the OSL reader. And the turntable basically goes back and forth in between the radiation source and the detector, so the photomultiplier tube and the LED lights. And it goes back and forth because you have to repeat several times the irradiation and then the measurement in order to produce a curve. And that curve that I'm going to explain to you in a short while, it's going to be the regeneration curve from which you're going to obtain your natural paleodose. So it's very important to have several repetitions in order to produce a more fine curve. So I'm going to start with how do you calculate the age? Because then you're going to understand the two, or I should say, there's three extremely important parts into an OSL age. The first one is the sampling. And the sampling basically depends on the expertise of the expert to understand the depositional environment, because you have to take the sample from a place that you know that is not going to be cohorted by underlying or overlying sediment. You have to choose it from your own little unit. Then you have another extremely important, so how well you sample is going to influence your paleodose, which is this little guy here. So your DE, your equivalent dose, we call it paleodose or natural paleodose. And then the other part of the equation is this very long sum of things, which are basically, they represent basically the dosimetry. So you're going to have to play with the determination of the dosimetry within the sediment using both the bulk sample and an instrument in the field that you're going to put into the hole that you make when you extract your sample, and you're going to obtain your field gamma dose. So basically what we're playing with here is alpha, beta, gamma doses, cosmic dose also, and you have to understand what your water content is and what the organic content is also during the history of deposition of your sample, or the burial history, basically. Elevation coordinates and overburden density and sampling depth are crucial also in the calculation of your age. So we depend on a lot of different factors in order to obtain a good age. So it can be very accurate and very precise if you do things correctly. And I cannot strengthen enough the value of knowing geology when you go into OSL, because then you're going to extract your sample better, because you're going to choose better your sampling point. And this is crucial. This is absolutely crucial, because we're going to see, or there's a lot of examples in the literature, unfortunately, that have tons of numbers of OSL ages that they don't necessarily worth a lot, because people are not careful enough to choose a unique layer or a unique facies within the context, the context of the deposition. So getting into the different parts of the equation a little bit more into depth, the fundamentals of luminescence dating are basically radioactivity. You have to have radioactivity happening all around your sampling point, so you can calculate that radioactivity and plug it into your equation. If there's no radioactivity, there's not going to be the electrons that are going to be trapped inside your grains of quartz and feldspar, okay? But also that radioactivity, those gamma rays and those beta and alpha rays are also very important in order for you to determine what's the amount of environmental radioactivity over your burial time. So there's different ways of approaching this. The further down the deeper you go, the more attenuated the cosmic rays are. So this is very important for those of you that are not quite experts in OSL. Never take a sample quite right on the surface, because then you're going to have to understand very well your cosmic ray influence and calculate it very well in order to have a correct age. So that's why if you go below 1 meter depth, then basically your cosmic ray, you can discard it in a way. Then comes the gamma that I'm going to explain in the next slide, but the beta and the alpha, basically those are the it's a big contribution to your dosimetry, and it happens at a centimeter scale. The alpha, and I cannot turn this, the alpha contribution, basically you can get rid of it during the preparation process with HF. So you etch the external part of your quartz grain or your feldspar grain, basically, and then you can get rid of it, so you don't have to think about it anymore. And then the beta, you can calculate it in the lab. So the alpha zone of influence, or the effective ranges of influence, it only goes to 30 microns. The beta is important because it goes 2 to 3 millimeters, and the gamma goes to 30 centimeters. So when you take a sample, for example, this big outcrop here, this is here in Spain on the western seaboard, and sorry, eastern seaboard. And basically this is a huge fluvial deposit, point bar, and then you have some alluvials at the very top. So the effective range of influence of gamma is 30 centimeters. So this is an example of a measurement of a gamma spectrometry in the field. And this is very important, and not a lot of people do it, or not a lot of labs, not all the labs in OSL have these kinds of portable machines. So that's why they always ask you, whenever you're going to take a sample, please also take some from the outer rim, those 30 centimeters, a homogeneous enough sample representing those 30 centimeters for the lab to prepare it in the, for the OSL lab to prepare it in the lab, to have the dosimetry done in the lab. It has to be as homogeneous as possible, because the more homogeneous, as in this picture here, the more homogeneous your deposit is, the more homogeneous your dosimetry is going to be, so there's less headaches. But if you have, let's say that this black grain here is a basalt, for example, and it produces a lot of uranium. If you sample very close to the basalt, then you're going to have an introduction of uranium that might not necessarily represent the time of deposition of your grains. The basalt is influencing it, so it's masking the real dosimetry. See? So the more homogeneous your sampling is, your lithology is, the more homogeneous your sample is going to be, the more homogeneous your dosimetry is going to be, and this is what we look for. So the basic principle of OSL is trapping. Trapping, so grains like quartz and feldspar, they have defects, what we call traps, inside the conduction and in between the conduction and the valence bands. These traps have different depths. And when radioactivity is produced, then you have all these electrons flying around that are going to be trapped in those traps or in those holes. What happens when they are exposed to sunlight is that all these electrons are going to be excited inside the conduction and valence band and be get detrapped and produce luminescence. So at that moment is what we call bleaching, because it's emptying the traps. So the sun bleaches the grains. The more the sun bleaches the grains, the more empty those traps are going to be. But there's traps that are extremely deep that might require a lot of time, a lot of sunlight time in order to be completely bleached. So this is why having grains in a very sunny environment is actually very good in order for you to have very homogeneous bleaching, which translates into very homogeneous and effective trapping, again, when the grains are buried. And that means that you're going to have a homogeneous age among all the grains that you collect from that sample that you take in that very sunny environment. For example, deserts, coastlines, and such. So the more turbid the waters are during the process of deposition, transport, and erosion, the less light they're going to see. So you're going to have a remnant effect, or you're going to have electrons that are not going to be able to get out, and that remnant energy is going to be seen when you collect that sample. So in luminescence, what we play with is different stimulation types. So, sorry, different minerals have different stimulation types depending on different wavelengths. In quartz, for example, if you see here the little black squares, that means that in that particular wavelength, it's actually very good for quartz to be stimulated because it's going to produce luminescence. So that's why we use for quartz, we use stimulating wavelengths in the blues and also in the violet. For feldspars, the best wavelength stimulation range is the infrared, so over here. There are other stimulation wavelengths, so you have to play a lot with optics and filters. But basically, this is what we use. Blue, OSL, violet, VSL, green laser is for single grains, and infrared IRSL for feldspars. TL, or thermoluminescence, only uses heat, so you don't have to pay attention to these optical wavelengths. In terms of age ranges, so right now, OSL can go, as I told you before, can go all the way to 1.2 million years. This is exclusively from if you use VSL. K feldspar can go all the way to 1 million years. And simple quartz OSL, or the routine blue OSL that we do, stretching it, we can go to 800,000, but it's more common to go all the way to 300,000 because there's a saturation effect in quartz when you use blue stimulation. And that saturation effect doesn't allow you to go further in the curve, the measurement curve. I'm just throwing here, like, for example, the age ranges for Raman series, terrestrial chondrogenic nuclides, and ESR, which are the methods that are often used to overlap or to compare independent ages with OSL. So, as I quickly told you before, what we need here is a good bleaching in order for grains to perform well and be sensible enough and sensitive enough for you to get that luminescence signal easily. So this is a pretty simple recycling cycle that we have in the surface processes. You have a moment of erosion, you have a transport until you have deposition. Okay. So as soon as you have a deposition, you start bringing in or trapping all those electrons and building in energy, okay? Until there's a moment that you're going to see sunshine, like you as in a grain of sand, you're going to see sunshine, and then all these electrons are going to get out, and you're going to deplete your quartz grain from electrons, from energy, and then it starts again. So it's a cycle of generation of the curve, and then detrapping, which is the zeroing or bleaching effect. And that goes on through history until you collect the sample. So it can take hundreds to thousands to hundreds of thousands of years. And this is what we measure, actually. So you can compare it here with the battery effect also. You have the batteries getting in, the battery is getting filled by the electrons, and then out of the sun it sees sunlight, and then you have a very rapid bleaching. And then you have, later on, when the little grain of sand gets buried again, you have gradual dose regeneration, and then again, when you measure it, that means you're exciting it with the LED lights. That means you're measuring the luminescence signal, so you have bleaching again. So you have the production of the decay curve. So what I'm going to show you now is a couple of videos for you to understand the importance of knowing your sedimentary environment, knowing your sedimentary processes, and be realistic about what your age or your OSL signal is going to be depending on the type of environment that you're going to sample, because not all environments are the same. So let me see if this is going to work. It should work. There we go. I'm going to, so this is a flash flood back in 2016, I think. So as you can see, this thing is pretty turbid. It goes down the stream very rapidly. It's a combination of a lot of silts and clays, but you can also see a lot of big boulders here. So imagine you being, I always tell my students, imagine you being a grain of sand. Where should you be in that mess of a flash flood in order for you to see the sunlight all the time prior to final burial? So it's quite impressive, and the more the waters are, the least bleaching or sunlight exposure you're going to get. So the worse your OSL signal is going to be. So the worse your sample is going to, your result is going to be. I'm going to skip this next one because I have a couple more here that are actually quite nice. This is the complete opposite. So this is what we actually want to have when your grain of sand rolling around a stream just prior to final deposition. So I found these in YouTube, but this is quite good because then you see a very nice movement of the grains. So imagine as if these were very fine grain sands. The water is pretty clear, so they're being bleached during the process, the transport process. And this is actually what we want, always. Like this would be the best for an effective OSL signal capture and, production of the regeneration curve and calculation of the age. So, and I'm going to show you what an Aeolian system looks like. This is also from YouTube. If it starts, oh yeah, it starts. So here you're going to see saltation and creep in coastal dunes from Oceanos in California. The water one, the previous video was in Alaska, in the Aleutian Islands. So here I'm going to forward it a little bit. Where was it? So anyway, so you can see these grains, there we go, rolling around and being completely exposed to sunlight, moving obviously, but eventually, because this is a modern analog, eventually they're going to be deposited in burial. This is the perfect process, or the perfect thing for us that we're looking for in terms of OSL. I wish everything was like this, so we wouldn't have problems of heterogeneous bleaching and all that nightmare, because then we have to apply a lot of statistics in order to get fairly good age. So this is brilliant. Okay, so I'm going to move forward. This is another example of perfect environment. However, these are bioclastic sediments. This is off the coast of Colombia in the Caribbean. And believe it or not, in these coral sands, bioclastic, there's a lot, or not a lot, there's quite some quartz grains in there that, which provenance comes from, I think, and this is what an experiment that we're doing right now, from the Saharan dust plumes, as the one that we saw a couple of weeks ago, that strong plume that came into the Caribbean. It can deposit grains of quartz, and very small, like clay silt size, in these types of environments, and you can actually pick it up with the an OSL reader. So why am I talking about all these, the importance of sunlight and bleaching processes? And it's because of this. Once you prepare your sample and you're measuring it, you are going to have basically, let's say, two types of samples, broadly speaking. Those with good bleaching are these, in which all these little grains, this is an actual discs, and this is actual real quartz sand. All these little grains, if they're bleached at the same time and buried at the same time, so they're going to have good bleaching and homogeneous bleaching, all those little grains are going to have the same age. But if you have partial or incomplete bleaching, then you go into this other image here. You're going to have grains that are going to be that are going to represent the real time of burial. Let's say that the real time of burial was 1,000 years ago, like the little blue dots. But then you're going to have a bunch of inherited signals that are going to give you ages much older than the actual real burial age. And this is the big problem in OSL. And this depends on the type of geological process and the type of sedimentary environment that you take your sample on. And this is something that people not necessarily think about. And this is my message to all of you. You have to think about where you sample and what you sample in order to avoid this partial or incomplete bleaching as much as possible, so we don't have headaches later in the lab measuring these samples. But not everything is perfect in life, so we have to deal with all these things. So that's why we use a lot of different statistical processes. In the end, what you come up after measurement is this: a series of curves, of regeneration curves, in which you're going to obtain your natural signal. So this is the first measurement, and these are the consecutive repetitive measurements that you obtain after irradiating the sample and reading it. And from this, you basically obtain your equivalent dose of your natural signal. And if you do a bunch of these, you're going to obtain histograms that or various stuff of representation that we can use radial plot, histograms, you can use frequency accumulation curves, like basically same as sedimentology. Think as grain size. And you can actually determine whether or not you have a multimodal distribution or a unimodal distribution. And this depends on the bleaching. So whatever I was showing you earlier in the representation of the little grains, this is it as you see it. So the better, the more unimodal your sample is, the more constrained your age and your error are going to be. So just to refresh a little bit the age calculation, you need the dose the equivalent dose on the top divided by your dosimetry. And this is to tell you that during preparations of samples in the different luminescence labs around the world are very different. And we're trying to come up with some kind of normalization of the preparation method, at least to have a minimum amount of processes or steps in order to ensure the quality of the sample. So this is an example of a luminescence lab. This was my former lab. I basically revamped it and acquire even multi-sensor core logger for cores. This is the first OSL lab in the world that has an MSCL in the darkroom. And the preparation procedure is quite simple, let's say, but it requires a lot of detail in the process. So you sieve it, there's a bunch of, you get your fraction, the fraction that has the most material, and then you apply a bunch of chemical treatments. And the final chemical treatment is HF to get rid of the alpha dose. And then you get all these pretty little grains that you can measure as multiple grains in one aliquot or as individual grains in a single aliquot disk. And this is also my former luminescence dating laboratory, the reader room or the measurement room, in which you can see here 1, 2, 3, 4, and there's another one up here, 5 RIIMS readers. The standard per lab is around 2 to 3. I managed to get 5 of them over the past 5 years. But anyway, it all depends like on the amount of money that you have in order to build one of these labs. And these are the types of grains, of discs that you use in order for measurements. So you have aluminum or stainless steel grains in which you adhere grains, quartz grains or feldspar grains, with silicon using these masks. So you can determine the size, the diameter of your disc, your measurable disc, or you have the single grain discs here that require a very precise green laser in order to find each one of those in this net. Calculation, well, there's a lot of Excel. Each expert has its own Excel spreadsheet basically, but there's a brilliant newish, it's 5 years old, application in the web, completely free of use, that actually I'm very inclined that all the labs use it when they do commercial work, because then you can actually plug in all the values that are given to you and obtain the age. This is the DRAC calculator from the Aberystwyth lab, and it's a really cool tool to have. And then yet again, if everybody uses the same tool, then you can compare everybody's results. So the key to success, this is a brief a summary of the key to success for an OSL age, is that you have to have the ability to measure and repeat and calculate the dose rate, the ability to measure the equivalent dose multiple times, separate pure and clean mineral grains in the lab, know where to sample exactly in terms of facies or geological context. And as in any good scientific method, you have to be able to reproduce your ages, your results, your intermediate data. And obviously, you have to be able to calculate your age within the statistically accepted models. So in terms of statistical uncertainties, the average that we're reaching so far is between 8 and 10%. The best right now is 5. The worst, 50. And this also depends on the type of environment. So the more, let's say, this goes also with the capacity of bleaching. So glacial environments are very difficult to date because apparently the pressure of ice changes the physical properties of the grains. And this is a phenomenon that we're not quite understanding quite yet, but it changes the sensitivity of the traps. And same as for fault zones. Fault zones can also apply pressure, and it modifies the traps, but also at the same time is if there's temperature generating those fault zones, then you can actually date those fault zones with OSL. So you have to understand all the different geological processes that are happening. So here, in terms of degree of bleaching of grains during transport, this is a very good image to show you what are the best sedimentary environments to sample and to date. So everything that is from this dotted line to up, those are the best environments. And everything that is from the dotted line below, those are the worst, or the ones that have the lowest capacity for effective bleaching, and the ones that are going to give you the more headaches when you produce the age or when you read the signals. In terms of sampling methods, I'm going to quickly go over the normal ones, or the ones that are more routinely applied. This is a loss profile. And as you can see, well, I'm under this sheet here, and basically it's a black tarp. It can be 40 degrees outside, and you are in the black tarp digging around like holes within the stratigraphy that you previously logged and know where to take your samples from. And here basically you do either do tube percussion, or you use a drill when they're extremely compacted sediments. Same goes here. This is Israel, a loss sequence in the Shoket archaeological site. This is a Chalcolithic site in which we didn't see, the loss was so homogeneous that you barely saw stratigraphy in these deposits. So I'm going to show you how we managed to see more stratigraphy using a portable OSL reader. This one down here, this is a trench that we dug in southern Portugal looking for tsunami deposits. And as you can see, like there's some tsunami deposits and storm deposits, like heavy mineral deposit on here. I'm down here under this UV tight sheet of opacite. This is used in window shielding. And this is Atapuerca, the famous archaeological site, prehistoric human evolution archaeological site that we have here in Burgos. And again, extremely hard material, so you had to use a drill in order to get the samples out from. Sometimes you cannot put in a tarp, you cannot get a core, so you have to go at night and basically excavate out the material from, because you cannot put in a tube. So you have to improvise. You have to know sampling methods, like geological sampling methods, in order to apply them in OSL. And different, as you well know, all these different types of coring methods are usable for OSL, are okay for OSL. Not all the experts, not all the labs use them or like to use them. They prefer the vertical profile and then putting in a tube horizontally into the sediment. That's the easiest way. And here, basically, the downside of coring is that you're not going to be able to get an in situ reading of your gamma spectrometer unless you have those very expensive IODP gamma spectrometers that go down the hole. So, and we obviously don't have those. They're very expensive. In terms of applications, as I told you before, archaeology, heritage, and culture, like we can date prehistoric sediments or prehistoric sites that have been infilled, like this cave in Bolomor. This is in Valencia. This is a Neanderthal skull was found right near the sampling site. Mortar, rock surfaces, bricks can be dated with OSL. Also, obviously, heritage buildings. Another example of the Atapuerca excavation site. This is again another Chalcolithic in the Negev, filled with loess that you can date easily. And obviously, all the geological, the geological applications. I'm going to show you here a couple. This was my PhD back in the States. This is the Florida, what we call the Florida Panhandle and the big Apalachicola Delta. And my task or my study was to reconstruct the evolution of these barrier islands. So I took several long vertical cores and determined, and obviously within the dunes and the beach ridges, and determine the progradation rates or erosion rates of all these barrier islands. One example here that I wanted to quickly show you is, and this is very common in the Panhandle or in the Gulf of Mexico, is that when you have, let's say, two dune ridges side by side, such as these ones, like you have the crest here of one and the crest here of the other and the trough in between. So to a couple of cores, and here you have an OSL age of 1300, then below obviously 1500, which is stratigraphically correct. And then on the next core down here, you have an age of 1600, which is stratigraphically correct. You are also on the foot of the dune. But then on the trough here, the core came out with ages around 1000 years ago. So this is to tell you that stratigraphically, not everything that you sample is in order. And that's when you have to know the different processes that happen in the area. Turns out that there's a lot of historical evidence of overwash during storm events in all of these beach ridges around the Panhandle. And basically here in the troughs, all the sediment accumulated from that overwash is being trapped there, hence the younger ages, and not on top of the dunes. Obviously, it doesn't go all the way to the top of the dunes, or they don't get preserved. One important factor when you are doing when you're sampling for OSL, when you're doing large studies of OSL, is that you have to check that all your modern analogs are actually zero. Meaning, when you're going to date a dune, all the different phases of a dune, obviously the newest part of the dune, the front dune and top of the crest, they have to have a zero age. Okay, so let's say like the 2 centimeters just below the top of the dune have to have a zero age. Otherwise, you're going to have a huge inheritance signal, and it's not making sense, because then the environment is not being, the sediment that is in that environment is not going to be bleached, or it's not being bleached. And you have to find a reason for that. These modern analog studies, they're not always checking them. Huge problem underwater too is the bioturbation by little animals, or even like on land by ants and bees or birds in the outcrops. Animals can burrow and mix sediment down to depths that you wouldn't believe. Like, for example, this little guy here, it can make holes down to almost 60, 70 centimeters deep. So when you're in the offshore environment, this is going to be a problem if you're taking cores to date something important. So the bleaching experiment, or to understand bleaching, basically, you have to understand what I called like the different histogram, the history in histograms. So when you have a lot of bleaching, very good bleaching, you're going to have the unimodal distribution, and it's going to be, it looks like this. If you have multimodal distribution, such as in fluvial environments, then it's going to be like this. So which one of these paleodoses are you going to use to calculate your age? And here, for example, when you have a very long skewness towards high DEs, then you're going to have a bigger overdispersion. And in this environment, which is typical of glacial fluvial environments, the only way that you can produce an age is by giving a minimum age. So you cannot give a finite numerical age because it's going, where do you choose in this histogram that your paleodose in order to calculate your age? So this little mess, let's say, it's what we use as a sedimentary proxy application, because each single environment can produce a different histogram. So for example, Hurricane Opal, it's this guy here. It's a 50 centimeter thick heavy mineral deposit. It produced an overdispersion of around 25%. This is the histogram, okay? Then we're moving to the Tohoku-oki tsunami in 2011, and the overdispersion was above 90. In this case, 90, like it could reach 100. But then we're talking about like all these different complicated overdispersions and histograms. You have to, one other thing that you have to take into account is that the event has to happen during daylight. If things happen at night, then you're not going to have bleaching. Then OSL, you cannot use OSL. So this happened in Mexico. I was called to date these two tsunamis, and basically the 1985 here, it gave me an overdispersion of 84%, which is normal for a tsunami deposit because it's very turbid waters. But then the 1979 one gave me an overdispersion of 151 and above. And that was due to its occurrence at night. So this was not a bleached event. And everything that I was measuring was inherited signals. So you have to understand that OSL might work, might be a very good tool and application, but not necessarily works in everything. And here's an example of sediments that are coming from the same geographical area that look exactly the same in terms of lithology, in terms of mineralogy and grain size, and they're all different because one was a normal marine deposition that had very nice unimodal histograms with 0 overdispersion. Then you have a tsunami deposit with 70 or over % of overdispersion. And then you have storms that can have an overdispersion of 50%. So this is the value of the luminescence signals.
Gloria, sorry to interrupt. We've
Yes.
reached the hour mark, so maybe we could ask about a 2-minute mark if that's possible.
Yes, I was going to go over the portable OSL stuff in 2 minutes, and that's it.
Fantastic.
Excellent. Sorry about that. So I wanted to show you what I call the sedimentary proxy application number 2, and it's the use of this little guy here, which is a portable OSL reader, which is fantastic for stratigraphical recognition and understanding the sedimentary processes. And what it does is basically you use a raw sample, I have it here, you use raw material, you put it into the apparatus, and the little thing has both types of light, infrared and blue. And it actually measures everything that you have in the sample, so quartz and feldspar together. That ratio can tell you actually whether you have more feldspar than quartz, and depending on the way the luminescence profile is generated, then you can actually read the stratigraphy. So an example here, and sorry for going so quickly, this is the loess that I was talking to you, the loess deposit in the chalcolithic type that I was talking to you about. So we thought that these were the different units. And as you can see here, these little dots represent the different RSL and blue OSL measurements. And what we saw is that they were in a zigzaggy pattern. Zigzag means reworking, because normal deposition only happens in this direction. So, and another example here, this is an offshore core taking offshore Israel, sorry for the redundancy, and as you can see in the different petrophysics profiles and MSCL sensors, we barely saw any difference, with the exception of this little area here. And in this little area with the PPSL measurements, we found a lot of reworking, and taking a closer look here, we saw, that basically this, we did a CT scan, this is an MTD, mass transport deposit at the very top of the core, only captured with the portable OSL reading stuff, as you can see here, the different grains, the different values. And last but not least, what I was telling you about the grains of sand moving across the Atlantic from the Sahara plume that got deposited in this bioclastic atoll. Basically what you can see is like all these zigzag here, these are peaks of quartz accumulation, very fine quartz accumulation within the bioclastic material. And their provenance is the Sahara dust. That's it, I'm done. Sorry for taking this long. Thank you.
No, it's fantastic. Thank you so much for your talk.
Many things, it was too much.
No, it's fantastic. It's a fantastic resource, and you know it will be very watched a lot, I'm very sure. Incidentally, the chat is open for questions, so please pop your questions into the chat for Gloria. And anybody who's watching this as a recording, on the anyone who's watching this recording, you can ask a question on the forums on the Seds Online website, and I'll be able to facilitate that Gloria being able to keep that conversation going, because this is a fantastic starting
point. There's too much. You know, there's too many applications in OSL that we can do, and too many ideas, basically.
Never too many, just enough. Great. So I'll start with some of the questions then. Okay. Let me have a look. Okay, so we have a question here saying, nice talk, Gloria. I want to know how accurate this technique is in dating diagenetic phases in clastic and carbonate rocks.
Well, it doesn't work with carbonate rocks. However, if you know that you have quartz grains, because feldspars are not going to be in these types of carbonate environments. If you have some kind of quartz grains or silica grains in there, they're extractable, and maybe you can date the quartz grains, but we can do, it doesn't work with carbonates. We need the trapping structure of the quartz and the feldspars, basically, in order to get injection of the electrons.
Okay. So a question then from Debbie saying, can you talk more about sample procedure? How much material is needed, and how do you clean the cliff face, and how deep must you take a sample from in the face? So sort of some do's and don'ts.
Wow, that's a long question. I mean, a long answer. Tube-wise, let's say that you're taking a simple tube. The tube should be preferably 20 centimeters long and between 5 and 7 centimeters in diameter. So it's a normal PVC tube from piping. But it also depends on how thick your layer, your target layer is, because you want the sample, the tube, to be inside and in the center of your layer. It cannot be in contact with the overlying or underlying layer. It has to be from the one layer only. So if your layer is, let's say, 5 centimeters thick, then you need a smaller tube, a smaller diameter tube. You can compensate by making it longer, thinking that theoretically the strata is going to deepen inside and be projected continuously. But then also you need a sample for the dosimetry part if the lab requires it, because sometimes labs use NAA in order to do the calculation of uranium and thorium potassium content. And with NAA, you can use the same sample from the tube because it doesn't require that much sample. But labs that have germanium detectors, for example, they require at least 200 grams only to do the sample for the germanium detectors. Okay, so it depends. So the first thing that you have to do is talk to the lab that you're going to send your sample to, because there's various requisites by lab, and different experts can be very picky in one or other things. I think I covered it all. I don't know.
That's great, thank you. Question from Ati. Thanks, Gloria, for the presentation on OSL dating. It's Ati from South Africa. I'm conducting my PhD research on possible paleo-tsunami deposits along our coast, and I'd like to use OSL to determine the ages of my sediment cores, since they are characterized by broken shells. So my question is, what is the best way to sample subsamples on split sediment core? Or would I need to resample the sites? And if so, how to deal with the issue of exposing them to light when cutting them?
Okay. So if you have the cores already, you have to prepare yourself a darkroom and cut the cores, the long vertical cores, in that darkroom environment. Talk to the Luminescence lab in Johannesburg. Or you can email me and I can give you more details. But the number one thing is like to implement a darkroom, split open lengthwise your core within that darkroom. Take 1/2 outside, because you're not going to see any structures whatsoever with red light. We don't focus, like everything looks the same under red lighting. Take one split half outside, do your logging, do your stratigraphy on that one, and determine at what depth exactly you want your samples from. And on the half that is in the dark room, that has never left that dark room, you can sample for your tsunami deposits in that half. So the problem is that you need to know the amount of quartz in the sediment. Because, for example, for my PhD, those dunes in the panhandle have 90% quartz. So I could take a slice, like a small 2 centimeters thick by the size or the depth of the half core, and that was enough for me to get 2 grams of pure quartz within the 90 to 180 microns, which is the target grain size for OSL. That's the best grain size fraction. So you need to know, if you have enough quartz, what grain size is your quartz, in order to determine how thick your sample from that tsunami deposit is going to be. Sometimes you will have to sample the entire layer of the tsunami deposit, and sometimes you have to sample just half. So it depends. But email me and I can give you more details about it.
Thanks, Gloria. Next question's from Diego, asking, thank you, Gloria, very useful presentation. Any ideas about the cost for setting up a complete OSL lab?
Okay, well, obviously, it depends on the country and the continent, obviously, because believe it or not, prices, even from the same company, I'm not going to say which company, are different in the Americas and in Europe. I found that out. A lab, what you need is, basically you need to build a classic sedimentology lab first with a chemical instrumentation or chemical facility. So you have to have a fume hood, all the sets for that. And then add in the OSL part, which is a dark room and all. Better to have 2 spaces, so your lab has to be big enough, or 2 separate rooms for all the readers to be in that other space. So I don't know, maybe technology lab can cost around 50,000 euros, more or less. Well, depends on the country and the continent. But the readers, bear in mind that one single reader can be around 100 to 200,000 euros, depending on the accessories that you're actually buying. Also, building up an OSL lab is not that simple, because the institute in which you're going to be establishing that lab has to have all sorts of required documentation in terms of nuclear facility, because each reader has a beta source, a radioactive source. So your institute has to be equipped to handle nuclear instruments, and that's the difficult part. That's the pièce of résistance, basically, because not every university wants to, or because it's costly, and then you have to have your personal dosimeters, you have to have constant checkups, like they're going to come and visit, and you have to, there's a lot of regulations around it. So, but anyway, so, but it's costly. It's quite costly, unfortunately. That's why every single age is expensive. OSL is not a cheap dating method, unfortunately.
Well, thank you. That's a great answer. We've got a question, another question from Ajit saying, "Hi Gloria, thanks for the nice talk. Apart from differential bleaching, what are main sources of errors, and how is error on age estimated?"
Well, there's a lot of, you have to think a lot. I didn't get into the dosimetry part because it's the most complicated part in OSL. And basically, the other errors can come from microdosimetry around your sample or around your grain, and understanding more the macro dosimetry. So that's the, let's say, the least understood area within OSL in general. There's some experts that are more keen into this, but I would say dosimetry has a lot of errors. I mean, not a lot of errors, like there's a lot of source of error coming from that dosimetry, within which also calculating water content and your water content history of the deposit. It's quite tricky to accurately say that, oh, this deposit or this, I don't know, this dune never had rained upon. So, and what about the water table? Has the water table fluctuated over time? You have to take that into account too. So we always put in a percentage of water content within the equation, and that percentage, if you get a wrong percentage, you can overestimate the age by quite a lot. Organic carbon content, the measurement or calculating the amount of organic content also is going to influence a lot your age. So these are errors that not a lot of people take into account, and we should be more strict and take more into account. There's a brilliant paper that came out 5 years ago about a general lab comparison that we did, an not intercalibration, but an intercomparison among several labs in the world that were given one sample. They were given the same beach sample, and you wouldn't believe the amount of difference that there were between the different labs at every single intermediary step towards the process of calculating the age. The difference in water content calculation was humongous. The difference in organic content calculation was astonishing. It was like all these little steps, different processes that you have to measure properly in the lab. Some labs didn't measure it, others over measure it, other labs did it right, other labs did it wrong. It's like, this is the importance of standardization. So there's many, obviously there's the systematic errors, also the machine errors and the intrinsic errors. So like you have to take into account many errors, and we always put in the equation, we increase the error with a percentage that we should put in order to account for all those systematic and erratic errors, let's say.
Thank you so much for that, and thanks to everyone here for asking such great questions and for the great answers as well. So I think with that, we'll give you a final thank you, and we'll say that next week we've got a talk from Joris from Utrecht University, who's going to be talking to us about deep water sediment deposition from hybrid contour turbidity currents. So that's a whole new, almost a whole new world. So come along and see us for that. And in the meantime, do come along to one of our coffee breaks. If you haven't been to one before, come along, say hi. We're a friendly bunch. And yeah, so have a look at the coffee break page on the website to see what time zone and group you would be able to come to. So with that, thanks again to Gloria, and see you all next week.